Thank you, Marco, and hello, everyone. So I will give my best and I will try to scream a little bit so that you can all hear and understand me. If anything is unclear, you can always raise your hand, or if I am too slow or too fast or too quiet, please tell me immediately and I try to change anything. So, welcome to this November weather briefing, and as you're probably a regular visitor of the weather briefings, you know with what I want to start. So, you see here the water vapor image, that's not the main, the most important thing at the moment, because here you see that's me. And I'm sitting here in the beautiful city of Salzburg in the middle of Austria. And what I want you to do now is take your pencil or anything you have, your arrow, and mark where you are from so that we get a good overview. Okay, yes, like Antonio is doing. So that we get a good overview to see where you're from and what the audience is like today. Okay. Many nice colors are appearing, so the arrows are all in different colors. It looks very nice. So I'll give you another 10 seconds time. And okay, so that is, okay, some more are appearing. Okay, good to see where you're from. And yeah, let's see what the weather is like these days. So let's switch to the next slide. So as you probably know, if you heard any of my weather briefings, I really like to start with a water vapor image because it gives you a good overview about the dynamics that are going on in the upper levels of the atmosphere. And you see we have here the water vapor 6.2, and you can see the atmosphere in an area between roughly 250 to 500 hectopascal with the help of these water vapor image 6.2. So what can we see? So we see some more distinct white shades, like for example here in this area there seems to be a frontal system. Also here you see some more whitish colors, which indicate some frontal systems. You see these black stripes, like for example here or here, which will be a sign or can be a sign for the jet stream, or the dark stripes are mainly localized on the cyclonic side of the jet axis. So with the help of this water vapor image, you can immediately say where the jet axes are. Then you see these blurrish patterns like over the Atlantic, like here. So there's a lot of water vapor in the atmosphere, but no frontal zone, as it's not as whitish as, for example, over here. So yeah, you can at least, with the help of the water vapor image, say something about the weather pattern in general, or the dynamic weather pattern. But if you want to go into more detail, you can use other products. You know it's now the 24th of November, so we're quite late in autumn. And autumn is mainly fog time. So you can't see fog with the help of water vapor images because it doesn't look deep enough into the atmosphere. So if you want to check the fog situation, there are many other channels you can use for this purpose. But before we come to that, I forgot I have here also the overall weather pattern, so the geopotential height in 500 hectopascal. You have an upper level low over the Iberian Peninsula, and in that connection you also have this frontal zone I have talked of before, this one here. You have a dominant ridge over the Atlantic, and also a very dominant high pressure system over Eastern Europe and Russia. And so you can think of what I want to say next. So in these areas of high pressure, there will be some more or less pronounced fog at this time of year. But let's see how we can check the fog. Which satellite images do we have to use? So classic is the high resolution visible image because yeah, it's high resolution, and if you have rapid scan, it's available every 5 minutes, and you see many detailed structures, so many more structures than you have seen with the help of the water vapor image. So you see this frontal zone here more pronounced, also this frontal zone over there. We haven't seen these low clouds, these water clouds, with the help of the water vapor images, and we also have not seen these clouds over here. You remember there was the high pressure system over there, and so you see different shades of white and gray. And yeah, if you have a trained eye, it won't be too difficult for you to answer the next question. So I just want you again to take your arrows, pick a pointer or anything, and show me where in this high resolution visible image, which was taken yesterday at 12 UTC. So where in this image can you see fog? Just take your arrow or a pencil and mark the spots where you see fog. Okay. Yes, Isabel, Jelena, you're both right. Yes. Also the pink one and the blue cross are right. Okay. Yes. I think you can't overlook this fog pattern over there. It's quite. I mean, if you think about the dimensions, that it's vast. So okay, that was just a warm-up question because it probably wasn't that difficult. The next question is, where in this image can you see snow? Okay, okay, yes. Antonio, Jelena, and the blue cross and the, okay. Okay, you're all experts. Any other location where you can see snow? I know it's a bit tricky now, as you can always see the names of the people pointing the arrow, but we're here. Okay, Andreas, yes. But we are here for training, so it doesn't matter whether you find the right location or not. Just try to find another snow spot, okay? Okay. I would like to add this portion over here, over Scotland. There is some nice snowy pattern, but you are all right. So you're really expert. So it isn't that difficult to distinguish between fog or snow, because fog has this really this smooth appearance, and so if you have a trained eye, it's not that difficult to find. And snow has the advantage that you see the land and surface features. You see all the rivers, like here or there. So that can help you distinguish fog from snow. Okay, so, but the problem is the fog and snow is not only there during the daytime when the high resolution visible is available, but if you're a forecaster, you also have night shifts, and you also need to locate the fog or the snow during the night. So for this purpose, there's, for example, the 24-hour microphysics RGB. As the name implies, it's available 24 hours a day, so you can use it during night and during day. It's the same image as we've seen before, but as it is an RGB image, you see so much more details in this one. So you see the fog over here appearing in this yellowish color. So it's not that hard to distinguish this from, for example, this thick, high-reaching cloudiness from the frontal zone over here. You can also see surface features with the help of the 24-hour microphysical RGB. I mean, you can't see snow, but you see that the surface has another color over Russia than it has over Northern Africa. So also the the surface temperature has an influence on the 24-hour microphysics RGB. So this is always nice because on the first glance you can say, okay, over Eastern Europe, this yellowish color, this is clearly fog, and over Western Europe, this reddish colors, those are really heavy clouds or thick clouds. So just a small wake-up question. So I hope you've all heard of the 24-hour microphysics RGB before. So you know that there are different satellite channels or different satellite channel combinations on the three color beams, red, green, and blue. And I now want to know of you which channels does this 24-hour microphysics RGB consist of? Of infrared and water vapor channels, only infrared channels, all three of the available channels, that means infrared, water vapor, and visible, or only infrared visible? What do you say? What is used for this 24-hour microphysics RGB? Okay. Okay. So don't be shy. I will give you some more seconds. Okay, 5 last seconds to go. You have 4 possibilities. It's like Who Wants to Be a Millionaire, but you won't get money in the end. So, okay. So, thank you for answering. It's only a wake-up question. So, as I've said, it's a 24-hour microphysics RGB. That means it's available 24 hours a day. So, it can't contain any visible channels. So the last 2 answers are definitely wrong, and it's tricky. The first 2 answers are a bit tricky, but in this special case, there are only infrared channels used. So all of you who picked the second answer, only infrared channels, are totally right. Okay, but as you see, you can clearly see the fog over here, but you can't see the snow. And if you're only interested in fog, it won't be a problem. But if you're also interested in snow, it's probably not the best choice. So what other options do we have? There's the day natural color RGB. I hope every one of you have seen this before. It's really nice. It's colorful. You see the earth and the weather in the colors you would think you would see it. So the ground, the soil is brownish, and the vegetated areas are green. And the main advantage of this RGB is that you can distinguish between snow and ice clouds and water vapor clouds. So you see that the low fog or the low cloudiness over here, it appears whitish, probably a bit pinkish depending on the height. And the thicker clouds, the heavier clouds, they appear in this cyan color, as well as the snow over here. What you also see very nicely with the help of this image are the rivers. So that's another, that can be another help if you want to distinguish between ice clouds and snow on the ground, because this can't be an ice cloud, as there is this river flowing through it. I don't know, is it the Volga? Something like that. So that also helps in this RGB image. So if you want to see a really nice image with nice colors, or if you have to give the satellite image to the media, to the press, this is probably the right choice for you to take. You also see the snow over Scotland quite distinct over here. So it's really nice image to use. So you see snow and ice clouds appear in cyan colors. And you have 3 color beams, red, green, and blue. So which color beam is missing? Okay. Probably the questions are a little bit too easy. And now you all know the right answer is red. Yes, it is red. And on the red beam, we have the near infrared 1.6. and it's on this color beam, there's nearly no reaction, or there's much more answer from water clouds than from ice clouds or from snow. Okay, so during the daytime you can use the day natural color RGB, and it can help you to distinguish fog and snow, fog and ice clouds, and things like that. So that can also be a choice when monitoring fog in autumn, when you also have the first snowy patches on the ground. So what more can we use? There's also the day microphysics RGB. You can see here the recipe of this RGB, and also in this, the advantage of this RGB is that you can not only distinguish between fog or low-level water clouds and thick clouds, but also snow has a different color, like you see over here. Snow appears pinkish, the water clouds appear this dirty whitish, and the high-reaching clouds, depending on how big the droplets are or how big the particles are, appear in these red-orange shades. So also the day microphysics RGB can be a really good choice if you want to monitor fog during the daytime. And there's also this benefit that you can clearly distinguish between fog and snow. Okay, if we now compare the three images, I have the three RGB images I have shown you. So the day natural color RGB, the 24 hours microphysics RGB, and the day microphysics RGB. In all three of them, you can clearly see the fog. In only two of them, you can see the snow on the ground. But there's a big difference. One of the images has another benefit. So what do you think of? What am I talking? What can you see in one image that can't be seen in the others? And I'm not referring to the snow, and I'm not referring to the fog. So which feature do you think am I talking about? Any ideas? If you compare the three images, is there any big difference? Okay, this question seems a bit too difficult now. Okay, for the sake of time, I will answer it myself. So in the day natural color RGB and the day microphysics RGB, you can't detect cirrus clouds too well. Wait a moment, I changed the color. In the 24-hour microphysics RGB, the cirrus clouds appear this blackish, in these blackish colors, like here over Denmark. And you can't see the cirrus clouds, neither in the day natural color RGB, nor in the day microphysics RGB. So always keep in mind that if the sky looks quite clear, for example, in the day natural color RGB, there might be some cirrus clouds which are not visible over there. So that's another benefit of 24-hour microphysics RGB. So you see every satellite channel, every satellite combination has its own benefits, and it's not good if you only use one combination or one channel all of the time. So it's just a reminder to switch to different combinations depending on the purpose you have. What more can you do when you want to see whether there's fog or snow or anything like that? You can use the NWCSAF Cloud Type Product. This is also available in the ePort, and this is a special threshold algorithm that is also using the cloud mask type, and in the end you get this quite gay picture with many colors, and you can see, so the fog is in these orange colors over here, and you can see, I don't know, the thick clouds are in the cyan color like over here, and so you get a quite detailed report about what you see on the satellite image. So this can be a big help if you're in the shift and you want to see, okay, where is fog, where is I don't know, whatever cloudiness you want to look at. So I really recommend you looking at this. If it's not available at your weather service, you can also find it at ePort, and more information can be found on the NWCSAF website. Okay, so now you know where fog is, you know where snow is, but you want to see, okay, how good is the model working at the moment? So you have here underlying the day natural color RGB, and above it you find the ECMWF low cloud cover. And you see, okay, there's here it seems to work quite well, but in this area the model does not seems to work not too good, or also in this area where we see the contrails, there are definitely no low clouds, and the model is saying, okay, this should be really covered with clouds. So that's always nice if you can compare the current situation and what the model thinks the current situation should look like. So it's just one quick look, and you can compare the analysis with the model. It's always good to give also a look to that. Okay, this loop, I'm sorry to say this loop does not work, but I have these two images instead of it. So we're still dealing with fog, and we're still dealing with the fog in this area over Eastern Europe. But now the date is another. So the previous images were all from yesterday, 12 UTC. These images are from Monday. And you see it was quite persistent weather situation. So also on Monday we had the high pressure system over Eastern Europe, and therefore this persistent fog. But what I want you to show in this image, and I hope you can see the difference because the colors are not too bright in this image now. But you have here the dust RGB, and the name implies something wrong because this RGB is much more powerful than just for detecting dust. You can also see cirrus clouds, or you can also see the moisture in the atmosphere. And if you take a really close look on the surface over here, it looks a little bit more bluish, and over here it looks a little bit more pinkish. I have to admit it's not that clear in this image because I had to make a screenshot and convert it and things like that. It's probably a little bit clearer here. You have these bluish colors over there, and there you have these more pinkish colors. And the pinkish colors are a sign for dry air masses. And it's a pity that the loop does not work because you see that this image was taken at 6:30. 6:30. Okay, I hope you can read it. This image was taken at 15 UTC. And you see that the fog dissolved quite fast, because the air was coming from continental Russia, and it's this really dry and cold air mass, and it really ate at the fog, and so it was disappearing quite fast. And you can see with the help of this satellite image that this was really dry air coming from Eastern Russia. So that's also one thing you can use the dust RGB for, to see whether the air mass is more moist or more dry. So if you have the possibility, take a closer look at this case at your local satellite images, because then you probably can see the color difference a little bit more pronounced. Okay, so as time flies, I just want to give you a quick outlook to the following winter months. I mean, now next week the meteorological winter is starting on the 1st of December. And I just wanted to give you a quick outlook what the ECMWF is saying about the next 3 months. And so here we have the seasonal forecast 42-meter temperature. And on this map of Europe, you can take a closer look at where you are coming from. So it looks that there's a really distant signal for southeastern Europe, or southeastern part of this map, that it will be quite too warm, and also for the northern parts. there's not that pronounced signal over continental Europe. Probably the Portuguese may suffer from this too cold pattern over there, but I think what looks really promising, or what looks really pronounced, are these features over the northern part of this map and the southeastern part. So there, the following 3 months may be really too warm. What about precipitation? What about possible snow? So in the northern parts of Europe, it will be too warm and too dry, whereas in the southeastern parts, there will be a little bit more precipitation than usual. So see it over here. For the other parts, there's no real, you cannot really make any, there's no distinct pattern visible in this image. And why is it like that? So you also have the most likely category of mean sea level pressure. You can all find this on the ECMWF homepage, and they're all freely available. All you have to do is just sign up for it. And here's the mean sea level pressure. And you see there's a positive anomaly over the northern parts. So that means there is, mainly too high pressure can be or should be observed in this region over here. Whereas the southeastern part of Europe or of this map will deal with lower pressure than usual, a lower pressure distribution than usual in these 3 months. So yeah, whatever you think of these seasonal forecasts, that is what the situation looks like. Nevertheless, I hope you have a nice winter season, because I think we won't hear us again this year, and so I wish you a nice Christmas season. And that's it from my part now, and I say thank you for answering all the questions, and I will give the microphone to Andreas now.
Yes, thank you, Lily, for your presentation. I want to give an extra goodie to you, something which I saw in the satellite images, and a phenomenon which is not which doesn't happen too often, which is not so common. It's Medicanes, and we had a Medicane end of October, and I would like to show you some images of this Medicane. So first of all, what is a Medicane? So Medicane is an artificial word which comes from Mediterranean and hurricane. So it's put together, the beginning and the end of these two words, and then we have a Medicane. Is it a hurricane or is it a cyclone? It's a little bit of both. For example, it shows an eye. You can see here, I point on the arrow. This is a Medicane from quite old one from 1995, and it shows here in the infrared image high cloudiness, and in the center of this hurricane Medicane there is an eye. So this is similar to the tropical cyclones, but this is, I think, more or less the only thing which is similar. Maybe the shape also of the cyclone. But otherwise, it's quite different from a hurricane. I have listed here the differences, and yes, Medicanes are a low pressure system. Okay, that's similar to hurricanes. They are also low pressure systems. They have a storm eye. I have already shown it on the image. They are often associated with heavy precipitation in the Mediterranean region. This is similar to hurricanes, but the wind speed is different. We have rarely wind speeds in Medicanes which are above 120 kilometers per hour. And one of the most important things is that Medicanes are symptoms of the lower troposphere. They are reaching the low and the mid-level troposphere, but do not reach the high troposphere, like for example hurricanes. In hurricanes, you will find the most intense winds near the center, near the eye. This is not the case for Medicanes. Medicanes have the maximum wind speed further up away from the eye of the cyclone. So they often appear in autumn. This is now the case. We have autumn. They are also appearing during the winter time. As much as no, never in the spring or in summer. You will not see them in these two seasons. What's necessary for the development of Medicane? We need some cold air from the north. So we need some sharp gradient, cold air in the north, warmer air in the south, or warm sea surface in the south. And we need a sharp gradient, a vertical temperature gradient of at least 57 degrees Celsius. The hurricanes need a very elevated sea surface temperature where they gain their energy from. This is not so much the case for Medicanes. A sea surface temperature of above 15 degrees is sufficient. So let's have a look at this cold air outbreak from the north. You see here the 500 hectopascal geopotential height and the wind arrows. So you see here from the north the winds blowing over France and arriving over the Mediterranean Sea. You see here the air mass RGB, which is not the best RGB to look at when we speak about Medicanes, because I told you it's rather a phenomenon of the lower levels of the troposphere. But nevertheless, we have some convection here, and we have a low pressure which is formed first in higher levels. So it's a cold drop which comes from the north and stays over the Mediterranean Sea. So this is 3 days later. This is the most intense phase. You will say, okay, most intense. You just see a little bit whitish clouds, but you see a lot of low-level clouds also. As I told you before, the air mass RGB is not the best RGB to look at, but I like it. And you see other things. You see, for example, this the red line, and this red line is a mark for the subtropical jet. You have the polar front jet here. It's not on the image, but imagine it's here coming down and going up to the north again. And you have here another branch of the subtropical jet. So remember what I said. This is the Medicane at its best. It's really intensely developed, and you will see it on this image much nicer. This is the high resolution visible image from 3rd October, 12 UTC, and you see all the clouds, mostly low-level to mid-level clouds. You see a little eye here in the storm center, and lot of convection embedded in this Medicane. I mentioned the sea surface temperature. Here's the forecast field of the mean sea level pressure. And we have sea surface temperature, which is still quite high at this time of the year, above 20 degree isoline, so it's about 20 degrees, 21, 23, and 22, 23 degrees. This is about the temperature of the sea surface. So quite high temperatures and a very strong gradient in the vertical. And that's why I have made some cross sections. Here you see the green cross sections from northwest to southeast through the Medicane, and you see here on the right hand side the 0 degree level about 650, 660 hectopascal, below very warm temperatures about 20 degrees, 18 degrees, and in the upper troposphere 400 hectopascal you have so minus 24, minus 30 degrees. So we have really a strong temperature gradient in the vertical. What else can we see in the vertical cross-section? The humidity here. We have the humidity in lower levels, then in between a very dry region, and above again some very high humidity. But the main humidity comes from the surface, from the sea, and is lifted up to higher regions in the center of this Medicane. And the lifting can also be visible when we look at the omega field. You have here the omega in the vertical cross-section, and you see negative values, which means that there's rising air reflected in the model fields. So what else? I have also seen that's the SCAT data, to really nicely show the sea surface winds. So this is the winds in 10-meter height, and superimposed to this air mass RGB of the Medicane, it really nicely shows the circular pattern of the winds. This is something you can see in your SCAT data or on ePort. If you go to ePort Pro, you can see the METOP SCAT R and SCAT B data. Both show this pattern nicely. So 12 hours later, it still looks very nice. We have the center here again, the white clouds, embedded convective cells, and the whole system moved from the Gulf of Genoa here over the Mediterranean Sea, across Sicily, and then was directed towards the Greek islands, towards here. And then with surface friction, you will see the next image, surface friction 12 hours later destroys the system, it vanishes and disappears. So the system was lasting for three to 4 days, which is quite long for a Medicane, but the maximum development was only shortly before it disappeared over the Greek islands. So this was a really nice phenomenon, which does not happen too often, and I hope you liked the image I have shown to you. So thank you very much. I give back to Lily.
Okay, thank you, Andreas. So now that's it. That was the November weather briefing. So the next weather briefing will be in December. And I thought that you, Andreas, would.
Yeah, yes. Sorry. I think it will be by the Hungarian. It will be done by the Hungarian Met Office. The date is not yet fixed, but it will be before Christmas.
Okay, so thank you everyone for taking part in this weather briefing. Sorry for the technical problems in the beginning. I hope you nevertheless enjoyed it. I hope my voice was loud enough for all of you. And so, yes, have a nice time, have a nice Christmas season, and I hope you will take part in the next weather briefing in the, let's call it Christmas edition. So have a nice time, have a nice day, and thank you for participating.
Yeah, I just see that Sophia posted the date of the next weather briefing. It will be the 16th of December, again 12 UTC, done by the Hungarian Met Office. So hope to see you then. Goodbye.